I'm pretty loud, so I'm assuming everyone heard everything I said, right? Great. Awesome. Okay, so why don't we just dive in? Oh, and so I just want to highlight some of my colleagues here, who my co-authors. So my name is Adam Aviv, and this was work done with Sungul Choi, Travis Mayberry, and Dan Roach, all at the U.S. Naval Academy. So what are we trying to protect here in ORAM technology generally is the metadata. So what do we mean by metadata? What is this kind of information, and why is it important to stop observation of this? Let me just give you an example of some metadata that is particularly interesting for ORAMs, which is the access pattern. So here is an access pattern scenario, kind of contrived, a classic example of this. So if you are a cloud provider, maybe you're a cloud provider for a hospital, and you're observing some interactions that are going on here. So all the medical records are stored in the cloud, and you went personally, maybe you went to the ER and you saw an ER doctor. This ER doctor is going to maybe look at your files, do a read and write on this. These read and writes of the files will be observed by the cloud, in which case maybe you need to go out to some other specialist, maybe like an oncologist, which will then also read this file. And now you have this situation where maybe the cloud provider, if it's observing this and is interested in learning some information about you, could learn maybe that you're being tested for cancer. And so what we have is a situation where the metadata, this access pattern, could actually reveal information in the cloud, even if that data is encrypted. It's not so much that the fact that the data, the actual record itself is revealed, it's the access on that data that is relatively important here. So one solution to this, and which was mentioned before, is ORAM technology. And the big idea of the way ORAM technology works, I don't want to get into the full details of this, is that it has this threat model where we're preventing the cloud provider from learning which files are accessed when. That's kind of the big scope of this. And so if we're going to translate that previous scenario, we would kind of set it up like this, and I organize it as a tree because this is the classic way we think about it in terms of path ORAM, where these doctors would use some sort of ORAM algorithm. We would reduce these read and writes to a single access, and some shuffling would occur on the tree such that you can't determine what was actually accessed and the actual files that were done. And this would work really well for like an Amazon setting. So everything's in the cloud, and you're doing some sort of request that's going to occur where you're going to download the documents, do some sort of like shuffling locally, and then re-upload things as you go along. What's actually interesting about this model that we observed is that in some cloud models, such as like Dropbox, which I'm assuming many of you guys use, it actually doesn't work quite like that. So instead of having kind of all your files in the cloud and you download them as you need them, you actually store a local copy of the information. And so if you're having a local copy of the files, then when you read a file, that just occurs locally. That's completely oblivious to the cloud. It doesn't know that you did this. So doesn't need actually protecting. It's when you actually update a file, when you actually write or change the contents of a file, that you need to do some sort of oblivious shuffling that occurs. And that's where we can do protecting. And there's actually a solution to this. This is called a write-only Oblivious RAM, and this was published at CCS in 2014. And just to kind of walk you through like the basic algorithm of how this works. So if we have all these files, that did not do what I thought it did. Let me go forward. There is no laser pointer on this, so I'll just point. So all these files that are here are local on your machine, and they are backed up onto the cloud. So notice that all these files are also encrypted, so there's no content that is actually going to be revealed to the cloud about the contents of these files. So if you're going to read a file A, well, you just read that file locally, completely oblivious, complete local operation. However, if you were to write or append to that file, like say write foo, well, we'll then take that file, store it somewhere else locally for a time, and at that point, the file has been modified, and now we need to obliviously write that back in some way to the cloud. So the way this algorithm works is that you're just going to choose 3 random blocks, and if there isn't so much content in there that you're going to get some empty space, we'll find at least one empty space in that block. We'll put the content in there. We'll then re-encrypt everything, at which point, after we've re-encrypted, this is a write, and Dropbox does its thing, right? It's just going to synchronize everything to all the other clients. And from Dropbox perspective, it doesn't actually know which of these files are written. It doesn't know where they are. So this operation actually can be oblivious. And what's nice about this, and typically we think about ORAMs in terms of their communication costs, is that the read operation here is just free, right? That's a local operation. In the foo operation, the writing of the foo to the file A, that's actually a constant communication cost because we're always going to touch the same number of files every time. It's not going to be logarithmic. So what are we doing in this work? What is the goal of this work? Is that we're going to try and take this write-only ORAM model, which is pretty well understood, and actually try and marry that in an efficient, practical way with Dropbox, such that we can actually build a real file system, a real oblivious Dropbox-like client. So that's what we're doing here, and we call this ObliviSync, and our goal is to adapt write-only ORAM to the cloud synchronization model. And I should say at this point that it isn't really about Dropbox per se. It's any system that has this kind of local caching, local storage thing. So, and the goal is to make it such that it seamlessly integrates with the file system. So if you're using this, you're just interacting with normal files, and there's some sort of translation that's going on that's synchronizing back to Dropbox or to any cloud provider in order for this to work. We're also going to provide strong security and an efficient design. We actually protect against timing attacks, which is somewhat new for this system. And we also have a small overhead of only about 4 times compared to non-private source, such as like a path ORAM. And we also handle variable size files, which is a challenge within ORAM models. And we also provide a realistic implementation using Fuse so that it like appears like a normal thing like Dropbox would normally in your file system. And you just modify normal files, and all that gets translated down the stack in an efficient way. So let me just walk you through the design of this system. So here's kind of a general outline of that, and I'm going to give you kind of a point-by-point thing here. So first, what we're going to have is we have these back-end blocks. So what you should think about these is these are just encrypted files that sit in a folder in Dropbox. So Dropbox does whatever it does. It's going to synchronize things whenever it synchronizes them. We're going to have a bunch of files. We'll call those blocks that are sit there, and they'll be encrypted. And they will be monitored by Dropbox normally. And so if they change, they'll get synchronized to some other client later on. Now, on top of that, we're going to layer something outgoing across here to the ObliviSync read-write end. So on top of those files, we'll layer kind of the algorithm, the Oblivious algorithm, that is going to do something like the write-only ORAM procedure. And it's going to then translate those and make those operations available, like reads, writes, to another layer, which will be the Fuse layer, which will then present all that information encoded in these back-end blocks, like a normal file system, to the front-end user. So if you're the user of this system, all you really see is just files that exist normally in the system, and it's going to get translated down. So if you do a write on some file, all that will get translated down, which will update some block, which will then get synced by Dropbox to some read end, which will then see all those updates naturally. So we're not actually going to change anything about Dropbox here. We're just going to build something such that Dropbox can do its own synchronization. So if you're going to, one thing you might be asking at this point is like, okay, that seems like a lot of work for a file system. Why not just use a write-only ORAM as a block device? Like we have solved file system writing to I/O. We use block devices for that. That seems like a really natural pairing. It turns out that if you go down that path, you find that it doesn't actually work the way you want. A lot of the efficiency of a system like this is going to be dependent on avoiding unnecessary writes. The writes are very expensive. So if you can design it in such a way that you can stage these writes such that you avoid them in these worst cost scenarios, you're going to get a lot of efficiency. Additionally, block devices don't really think in terms of variable size files. And if you want to have obliviousness with variable size files, you need to do a little bit more work. So it actually makes a lot of sense to actually pair kind of the file system nature, the design of the file system, with the Oblivious backend writing model. So let me kind of walk you through this model in terms of the terminology. So we're going to start with the same kind of blocks that are going to exist in the back end. They're all going to be encrypted. And then we're going to split them up into what we call split blocks. So we'll just have a top half and a bottom half of these, and we'll assign each of them a number. This is just so we can figure out where is what. And we'll call these numbers block identifiers. So we have a split block with a top half and a bottom half, and they each have a block ID. Then we'll have this super block, which will be our mapping of what we'll call file IDs to what blocks they're living in. So this is part of the file system. So a file ID represents something that's a file in this system. And then these are each going to be mapped to a back-end block. And we'll keep this mapping information in the super block. So that's always going to occur at block 0. The super block will store this mapping. And then we also need to present these file IDs as file names. So we'll actually have another block, which will be the directory entry, which will be file ID 0, and that will be presented to the user, so we can find the file names to match to file IDs. You'll also notice in this diagram that the individual files themselves, so 4, for example, file ID 4, is split amongst many different blocks, and that's the file segments themselves. And a file segment can fill up an entire block, a half a block, or some other smaller portion, and these things are going to be able to move around, which is why we need all this mapping technology. So the way this system is actually going to work is that we're going to keep kind of two major parameters. The first parameter is going to be the drip rate. So the drip rate is going to be how many blocks for each write are we going to shuffle. The drip time is how often are we going to do this operation. And since we're doing this in some sort of staging operation, we're going to actually maintain a buffer of staged writes that are going to occur. And the buffer is going to be at the top here. So let me walk you through this process. So the first thing that will happen is maybe we want to create a new file such that it gets file ID number 6. Well, this will, and then we write to that file. This will actually appear in the buffer. So this is also local. So we can just store it there, and if we were to access it at some point later, or like write again to it or read from it, it will just occur in that buffer. Now, if we were to open another file, such as file ID 5, which is, and then write for append, well, we're going to evict it out of this spot, but we're not going to actually overwrite it. We're just going to move it into this other buffer, and this, again, is all occurring locally. And then we can append to it and change it so that if we were to read from it again, well, that will just occur in the local buffer. Again, this is oblivious and not available to the cloud provider. Then at some point, our timer is going to go off, and then we're going to have to take all these staged writes and actually write them back to the blocks, re-encrypt it, so that it then can be synchronized to other clients. So we're going to use pretty much the same algorithm I showed you before. We're going to choose 3 random blocks, and we're going to evict everything out of those into the buffer so that we can do some sort of packing routine in order to put them back in. And we're going to have a couple different packing rules. So the first rule is that if we have a file segment that's a full split block, so it fills up an entire region, we're not going to make that move, and this is for efficiency purposes. But smaller files, files that are smaller than a half split block segment, they can move between the top halves, and this way we can pack and avoid a worst case scenario in terms of just efficiency. And so what we end up with is this kind of packing here, in which case then we can re-encrypt everything, and then that gets synchronized back to the server. But of course, now things have moved around, so we have to also re-encrypt the superblock, which stores this information as well. And you may be wondering what happened to 5. So 5 over here is still there. We didn't actually write that block, but that information is now stale. And we can actually easily figure out whether or not information is stale by doing a reverse lookup in the superblock. So all that kind of works together. So just to kind of summarize these design settings. So what we have here is a specialized file system that's going to be embedded within a write-only system. And what I didn't get to show you is that we do have this fused front end. So if you were using this system normally, what you would have is just the files. They would have normal names. They would exist as normal files in the system. And it would be mounted. For those who don't know what Fuse is, it's a file system in user space. So it's just going to capture all the read and write calls and be able to like mimic a normal file system. But really what's going on is the write-only ORAM is capturing those calls and doing these operations. And we're going to synchronize the cloud at these regular intervals, which we'll call epochs. And we're going to buffer the writes in between, and then we're going to synchronize these events every once in a while to do repacking and do the oblivious operations. And this is what's going to prevent timing attacks. So that's going to be kind of novel for this space. And we're also going to have multiple clients. So for right now, our current implementation, we only allow for one reading and writing client. So only one of the clients can read and write at a time. And then any number of clients out there can get these synchronizations as they occur. And we can easily tune to different settings. So this is actually something that's really interesting. So I've been talking a lot about Dropbox, but I also said synchronization and backup. So the Dropbox model is where you want things to kind of occur relatively frequently. So maybe you want to set a drip rate to like just 3 blocks at a time, but you want to do it frequently. But if you're doing this for backup, you can imagine a scenario where I just want to back up some large settings of my file system once a week. Well, then you'll be willing to transfer more information so you can do larger drip rates, but your drip time can shrink. And another thing that's really nice about this is that it isn't really dependent so much on one particular provider. You can actually tune it to other providers. So it turns out Dropbox uses 4 megabyte blocks. Other providers use smaller block sizes in terms of how they like to do transfers, so you can actually match it up. So there's a lot of tuning parameters that are pretty good here. So just to kind of walk you through the results, I'll show you just one major result, which is our latency result. The way this experiment is set up is that what we're interested in is like as we keep adding files to the system one at a time, and as these blocks get full, what's going to end up happening is it's going to just get full and fuller and fuller. So as we start to randomly choose blocks to write things back to, there's going to be less empty space. So we're going to be stuck where we may not be able to clear things out of the buffer. We want to know how this performs over time. So here's kind of the basics of this result. Let me walk you through the graph. So just to give you a setting, so we're assuming 1 megabyte blocks, and we're going to insert about 90% full. So it would be 90% full, so it's going to be hard at the end. You can kind of see where that challenge comes from. This is going to be our drip rate settings here. So you can see we use different drip rates. And at the bottom here, this is how full it gets. So theoretically, we were able to show that at 20% full, we should always make progress. But as you can see from the larger state of this graph there, you actually do much better for quite a bit more time. And it's kind of in 2 different stages. So the first stage, you seem to always make progress all the time. So every time you do an oblivious write operation, you're clearing stuff out of the buffer, and you're not having to wait another epoch until the next time, or you might get lucky and find some empty space. And then as you get around 70%, things start to deteriorate rather quickly, and you start to have problems where you need multiple epochs to get there. But I'll point out that this graph only goes up to 5 epochs, just 5. And let me give you some numbers to match to those epochs. So if we have 1 megabyte blocks, we're talking about a 1 gigabyte worth of space on your Dropbox to do this. A drip time of 30 seconds, which seems totally reasonable, and a drip rate of 3 blocks per epoch, well then at 90% usage, like kind of a worse, really bad scenario, I mean, you're still getting your thing synchronized like every 2.5 minutes. And I think most people would be okay with that for Dropbox. So it kind of works in a lot of different scenarios. Now, we have lots of results in the paper. I encourage you to read it, including running this on Dropbox and doing comparisons there. And so that's kind of cool. And just to kind of give you some takeaways, if you're interested in more, so we really believe this could be a practical system. And it does oblivious reading locally and does these writes going back to the back end. We have a small communication overhead of 4 times. We can handle variable size files. It's not going to be susceptible to timing attacks because we're going to use this epoch. It's tunable to different applications. And we do have a real implementation on Dropbox that you can actually use if you're interested. So I want to thank you for your time. My name is Adam Aviv, and we are at the U.S. Naval Academy. Please check out our code repository. Don't actually use it, but you should check it out. And we do have a YouTube video of this working if you're interested in that demo. Thank you.